Now, let us look at an application of our constant volume specific heat. Let's consider a piston cylinder device that contains helium gas at a pressure of 150 kPa, a temperature 20 degrees centigrade, and a volume of 0.5 cubic meters. The gas is compressed in a polytropic process to a pressure of 400 kPa and a temperature of 140 degrees centigrade. We are going to assume our helium gas satisfies the ideal gas law, and we're going to take our gas constant as 2.0771 kJ per kgK, and our constant volume specific heat as 3.116 kJ per kgK. We want to determine the work into or out of the system during this process, as well as our heat loss or gain. For us to begin, we are going to list our information at state 1, and then we are going to list how we go from state 1 to state 2, and list our state 2 variables. At state 1, we have a volume of 0.5 cubic meters, a pressure of 150 kPa, and a temperature of 20 degrees centigrade. We move in a polytropic process to state 2, where our volume is unknown, but our pressure at state 2 is 400 kPa, and our temperature is 140 degrees centigrade. For us to determine our work into or out of our system, we need to determine our volume at state 2. And to do such, we are going to use the ideal gas law. Since our mass is constant and our gas constant is constant, we are able to determine our volume at state 2 via the ideal gas law. That is, our pressure times our volume at state 1 per our temperature at state 1 is equal to P2V2 per T2. This means our volume at state 2 is equal to our volume at state 1 times our pressure at state 1 per that at state 2 times our temperature at state 2 per state 1. Or we'd have 0.5 cubic meters times 150 kPa per 400 kPa times 413 Kelvin per 293 Kelvin. Or our volume at state 2 is 0.264 meters cubed. Now, we need to find our polytropic index N for us to determine our work. And if we recall, our pressure times our volume to the N is equal to a constant, we can solve for N. N is equal to the natural log of P2 per P1 per the natural log of V1 per V2, where we'd have the natural log of 400 kPa per 150 kPa per the natural log of 0.5 cubic meters per 0.264 cubic meters, or our polytropic index is 1.53. Thus, we can use our formulation of work based upon our pressure and volume at state 1 and 2 and our polytropic index N. Our work from state 1 to state 2 is P2V2 less P1V1 per 1 minus N, or we'd have 400 kPa times 0.264 cubic meters minus 150 kPa times 0.5 cubic meters per 1 minus 1.53, or we'd have minus 57.75 kilojoules. The minus sign indicates that we are supplying work to our system during our compression process. Now we can rearrange our conservation of energy equation, neglecting kinetic and potential energies to solve for heat. That is, our heat supply going from state 1 to state 2 is equal to our change of internal energy, U2 less U1, plus our work going from state 1 to state 2. Or this would be equal to our mass times our specific internal energy at state 2, less our specific internal energy at state 1, plus our work going from state 1 to state 2. If we recall our expression for dU based upon our constant volume specific heat, we can say U2 less U1 is equal to the integral from state 1 to state 2 of CV dt. Or this is approximately equal to our constant volume specific heat times T2 less T1, assuming that CV is a constant value. Now, we have to solve for our mass such that we can determine our change of our internal energy, which can be done through the ideal gas law, either evaluated at state 1 or state 2. Our mass is equal to pressure times our volume per R times T. Or, at state 1, we'd have 150 kPa times 0.5 cubic meters per 2.0771 kilojoule per kgK times 293 Kelvin, or we'd have a mass of 0.123 kilograms. Finally, we can express our conservation of energy equation as Q from state 1 to 2 is equal to our mass times our constant volume specific heat times T2 less T1 plus our work going from state 1 to 2. We have all our known quantities that we can substitute in. We have a mass of 0.123 kilograms. We have a constant volume specific heat taken as 3.116 kilojoule per kgK. T2 is equal to 413 Kelvin. T1 is equal to 293 Kelvin. And our work was minus 57.75 kilojoules. Thus, our heat is minus 11.76 kilojoules. The minus sign in front of our heat implies that heat is removed during our compression process. The minus sign in front of our work indicates we are putting work into our system. Now, it is noted we used a constant volume specific heat of 3.116 kilojoule per kgK. Our constant volume specific heat for various substances can be found on table A5 on page 760, where we have CV naught, We will talk about what the knot means when we talk about our specific heats for ideal gases later. However, we recognize that this matches our specific heat value used within this problem.